So far we have discussed what is a series of complex numbers, and we discussed different tests for checking the convergence or divergence of a given series. Now in this discussion we are going to discuss very basic and important test for checking the convergence or divergence of a given series of complex numbers. Now it is known as D'Alembert's ratio test, or just commonly known as ratio test. Now what is this test? So it is a very simple test, and in this test, if we are given this series of complex numbers, then we calculate this limit. So what is this limit? We take the n plus 1 term, we take its modulus, and then we divide it with the modulus of the nth term, and then we calculate this limit. And if we can calculate this limit and is equal to L, then there are conditions on L under which the series converges absolutely or diverges. Now if this L is strictly less than 1, then we say that the series is absolutely convergent, and if this L is strictly greater than 1, then we say that the series is divergent. Now this test doesn't say anything when L is equal to 1. So when the limit is equal to 1, when the limit of this expression is equal to 1, then we say that the test fails, or the test is inconclusive, or doesn't say anything about the convergence or divergence of a given series. So when this happens, when L is equal to 1, we try to apply some other test or some other strategy for checking the convergence or divergence of a given series. Now the proof of this ratio test is very similar to the proof for the case of real numbers. In fact, it is exactly the same. Okay, so I'm leaving this as an exercise for you to have a look at the proof for the case of real series, the proof of the ratio test, and then write it down for the case of complex. Now let's apply this test for checking the convergence of this given series of complex numbers. Now over here, the nth term is equal to 1 minus iota raised to power n over n factorial. Now what do we want to calculate? So we want to calculate limit n approaches to infinity, this n plus 1th term and the modulus divided by the nth term. Now let's write down the n plus 1 term. So the n plus 1 term is 1 minus iota raised to power n plus 1 divided by n plus 1 factorial, and the mod divided by the modulus of the nth term. So it becomes 1 minus iota raised to power n divided by n factorial. Okay, and of course we are calculating the limit n approaches to infinity. So this is equal to limit n approaches to infinity. So we can write it down, the numerator, in the following way: 1 minus iota raised to power n plus 1 divided by n plus 1 factorial. Okay, so the modulus of this. And similarly we can write down the denominator in the following way: n factorial divided by 1 minus iota raised to power n and the modulus. Now we can cancel out these two things. Okay, of course, if we cancel out these two things, then we will be left with, in the denominator we will have n plus 1, and when we cancel out these two terms, then what do we get? So we get 1 minus iota, and of course the modulus of 1 minus iota, and the limit will remain the same. So limit n approaches to infinity. Now what is the modulus of 1 minus iota? So the modulus of 1 minus iota is square root of 2. So limit n approaches to infinity, square root 2 divided by n plus 1. Now square root 2 is a fixed number, and when we take n approaches to infinity, then the answer is going to be 0. So L in this case is equal to 0, and of course which is strictly less than 1. So this implies that the series by ratio test, this series 1 minus iota raised to power n over n factorial, n varies from 0 to infinity, converge. Okay, so this is the final. Now let's apply this ratio test on this kind of complicated situation where the terms are involving this z. So this z is kind of variable here. So when we change the value of z, if we take z is equal to 1, then it will be one series. If we take z is equal to 2, it will be the other series. And if we take z is equal to 1 plus iota, it will be another series. So it is not just one series, these are infinitely many series, or it's a series which is a function of z. Now we want to show that for these values of z, okay, for these values of z, the series converges and it diverges for these values of z. So whenever the modulus of z minus iota is less than 2, then this series converges. Okay, so whenever we take z such that z minus iota modulus is strictly less than 2, then this series will be converging. And whenever we take a value of complex number z such that the modulus of z minus iota is strictly greater than 2, then this series will be divergent. Now let's see how we can use this ratio test to prove this result. Okay, so in this case, what is the nth term? So the nth term is going to be equal to z minus iota raised to power n over 2 raised to power n. Okay, so what do we want to calculate? So we want to calculate this limit n approaches to infinity of the modulus of the n plus 1th term divided by the modulus of nth term. So this is going to be equal to limit n approaches to infinity. So n plus 1 term is going to be equal to z minus iota raised to power n plus 1 divided by 2 raised to power n plus 1, and of course the modulus divided by the modulus of z minus iota raised to power n divided by 2 raised to power n. Now of course this is going to be equal to limit n approaches to infinity z minus iota raised to power n plus 1 mod divided by 2 raised to power n plus 1 mod, okay, and multiplied by of course 2 raised to power n divided by the modulus of z minus iota, okay, and power n. Now what will happen in this case? So this 2n will cancel out this 2n and we'll be left with only 2. And what about the other case? So in this case, this will cancel out with this and we will be left with z minus iota mod. So this limit becomes, so this is equal to limit n approaches to infinity mod z minus iota and divided by this 2. So what will be the limit in this case? So this is going to be equal to limit n approaches to infinity. Okay, now we can see that there is no n in this case. So this expression is independent of n. So this implies that this limit is going to be equal to z minus iota divided by 2. Okay, now this is or L in this case. And we know that by ratio test, when L is less than 1, then the series converges, and when L is strictly greater than 1, then the series diverges. Now let's see how to get our desired result. Okay, now z minus iota divided by 2 is basically or L, and we know that when L is strictly less than 1, this implies z minus iota mod divided by 2 strictly less than 1, and this implies z minus iota modulus strictly less than 2. So this is the case when the series converges. And of course when L is strictly greater than 1, this implies z minus iota divided by 2 strictly greater than 1, and which implies z minus iota modulus strictly greater than 2. And when L is greater than 1, strictly greater than 1, then the series diverges. So we have got our desired result that whenever z minus iota modulus is less than 1, that the series converges, and whenever the modulus of z minus iota is strictly greater than 2, then the series diverges. So that's how we use this ratio test in this kind of complicated situation where the terms of the series are functions of z. So it is, in fact, we can say that it is a complex valued function. So this example gives us a kind of support to our idea that we are going to define new complex functions using the concept of series. So over here we just did it. We defined a function, and we also found a condition for what values of z this is going to be convergent. In other words, for these values of z, when the modulus of z minus iota is strictly less than 2, for these values this function is going to give us some complex number. And of course, for these values, when the series is divergent, it is not going to give us a complex number, and it is going to be infinity. So this function only makes sense when the modulus of z minus iota is strictly less than 2. So that's how we kind of define new complex valued functions using the idea of series. So in this discussion, we discussed what is a ratio test. We also applied this test to check the convergence or divergence of a series of complex numbers. And most importantly, we discussed an example where the series was the terms of the series were kind of functions of the variable z, and this gives us an idea how we are going to define new complex valued functions using this concept of series.